Welcome to an adventure of the mind. It begins by looking ahead to the sights and sounds of the mechanical universe.
There are certain human activities that the mind associates with a particular place because it's somehow more special, more elegant there. For example, I'm not inclined to gamble, but if I wanted to, I wouldn't go and play poker in some sleazy back room. I would take the Concorde to Monte Carlo, put on my tuxedo, and play roulette in the casino. In the same way, when I think of tennis, I think of Wimbledon. For horse racing, it's the Kentucky Derby. For opera, it's La Scala. And for physics, if you want to study physics, the place is Caltech. That's what we're here for. Let's get started.
There is a branch of science, cosmology it's called, that concerns itself with the past, present, and future of the universe as a whole. How did that universe begin? How has it evolved? And where is it going? There is another branch of science, in the realm of physics to be exact, which is called mechanics. The science of mechanics concerns itself with something not quite as philosophical, perhaps, but no less profound. However it started, and wherever it's going, how does it all work? From the smallest particle to the largest cluster of galaxies, what keeps it all going? Whether it's speeding up, slowing down, changing direction, or cruising straight ahead, why does it all behave the way it does? Whether it's a solid, a liquid, or a gas, or an enigmatic unseen force, just how does it all interact? And why? All of these questions, from the simplest to the most profound, are by no means late arrivals. In one form or another, they've been around as long as there have been people to ask them. Even the earliest human inhabitants of this planet must have looked up at the sky and across the landscape and asked, how does it all work? And without even knowing it, they had taken the first tentative steps toward discovering and understanding the mechanical universe. If there is a key to understanding the mechanical universe, it can be found in the realm of mathematics. And among early civilizations, there were no greater mathematicians than the ancient Greeks. The work of Greek mathematicians added immeasurably to the advancement of science. In the area of circles, for example, they worked to the point of exhaustion, which is precisely what it took to find the number pi. But despite, or maybe because of, such brilliant discoveries, the Greeks fell behind. Once the Golden Age was over, they placed a lower value on the questions than on the answers. So, with too few questions, the world bought Aristotle's mechanics, with Plato's ideals, and eventually Ptolemy's solar system, in which the planets orbit the Earth uniformly, circles on perfect circles, was held aloft by conventional wisdom. Answers instead of questions, that went almost unchallenged well into the Renaissance. The intellectual direction of Western civilization had fallen into line behind the endless circular argument of the Platonic ideal. The question isn't really why, unless it's why tamper with perfection. The question is how. How, 1,500 years after Ptolemy, was the perfect circle broken? And in what must seem another contradiction of logic, how did an orderly new world take shape in the crucible of scientific revolution? It began when an extremely curious Polish monk, Nicholas Copernicus, looked toward the stars and saw things in a different light. Among other things in the Copernican solar system, the Earth orbits the Sun rather than the other way around. Why did Copernicus see the universe this way? And from a scientific point of view, how did such a vision make him the world's first revolutionary? An intellectual bridge that had spanned thousands of years waved precariously in the winds of change. Pillars of an age-old academic community were beset with threatening questions. No one was better equipped to fill the intellectual void than Galileo Galilei. Though Aristotelian thinking still ruled the world of the Italian Renaissance, Galileo was an exception to the rule. He was a Copernican with the courage of his convictions. In other words, he had the right idea at the wrong time. Fine, said his critics, an army which arose in defense of the status quo. But if the Earth really spins, why does a ball, dropped from a tower in Pisa, for example, land directly below? Why not in the next city-state? For a change, the answers were more dangerous than the questions. The Church, which considered him both a threat to Rome and an affront to common sense, warned him to leave things in their proper places. Nonetheless, in practice and theory, Galileo spoke the truth and proved what seemed to be the impossible. And when all was said and done,
well, in my left hand I have a feather. In my right hand a hammer. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Galileo's findings are not only correct, they come down through history as an amazing example of the scientific imagination at work. With his brilliant mind set on explaining the universe in scientific terms, Galileo's experiments led him to discover the law of inertia. With uncanny physical insight, he accurately envisioned the parabolic path of projectiles, as well as the law of falling bodies. Even today, when they come right down to it, the questions behind these experiments are as challenging as they were 3 centuries ago. How did Galileo calculate a projectile's path? And by doing so, how did he begin to propel mathematics deeply into the future? In the days when seeing truly was believing, how did he disprove the obvious perception about falling objects? How can a hammer and a feather land at the same moment? And as Galileo himself fell from grace in 1633, why was the whole business of the universe a trial to everyone concerned? About the same time, every day was something of a trial to the wandering mathematician, Johannes Kepler. To a man in almost constant flight for his life, a life of illness and poverty, the loss of love and loved ones, witch hunts and the even meaner spirits of his associates, simple existence was something of a challenge. Surely, no man ever sacrificed more to grasp the scientific truth. But on the other hand, no man's discoveries ever proved more rewarding than Kepler's laws. The law of ellipses, the law of equal areas, and Kepler's third law of planetary motion, the law of harmony. With his laws of planetary motion as the key, Kepler entered the secret chamber of the cosmos. And yet, by explaining how rather than why the solar system works, he was destined to remain on the threshold of the mechanical universe. It was time for someone else to come along and take the final step. On this very path, which led directly to the moon, along came Isaac Newton with some crucial questions of his own. Why does an apple fall? Since an apple falls, why not the moon? If an apple and the moon fall for the same reason, why doesn't the moon, like the apple, crash crash into the earth. With such questions, the questions of a lifetime, Newton rather calmly sat down and piece by piece destroyed beyond repair the age-old machinery of the Aristotelian universe. And then, with answers that were equally astounding, he created something to take its place: the mechanical universe. The mechanical universe, a predictable, orderly universe, obeying precise mathematical laws. And, with the laws of motion, the ability to take on almost any physical challenge. With his laws of motion, not unlike David confronting Goliath, Isaac Newton took on the great issues of mechanics. Armed with his keen mastery of forces, a precise knowledge of trajectories, and the universal law of gravitation, Newton mastered more than any human being before him. And for that, he deserves serious attention and considerable fanfare. Nonetheless, in science, answers are part of the past. The future belongs to the questions that science raises. Which means that even Newton's laws were only a beginning in the right direction. For example, in modern times, a projectile can be guided with mathematical precision. How is that done? Part of the answer is an instrument called the gyroscope. How does it work? And in the all-encompassing mechanical universe, why is even a bicycle wheel a kind of gyroscope? Angular momentum is a key to the answer. But what is angular momentum? And why does it turn out to be so vital throughout the universe? From the cutting edge of the most distant galaxy to whirlpools in the family bath, angular momentum moves in all the best circles. And among other things, moving in circles is the key to keeping perfect time. Few things govern as steadily as today's mechanistic concern with time. However, while people now have more time on their hands, the preoccupation with it is hardly a recent phenomenon. What is comparatively recent, however, is the phenomenon of accurate time. It came about gradually, day in and day out, for 4,000 years. It finally arrived, with an understanding of harmonic motion. What is harmonic motion? And when it comes right down and up to it, how does harmonic motion really work? And going full circle in the mechanical universe, how is it related to circular motion? The answer isn't as mysterious as it may seem at first perception, and there's no reason to approach it in a roundabout fashion. However, sometimes it helps. All it takes is a little differential calculus. While Isaac Newton's calculus goes far and wide throughout the mechanical universe, the scope of his generosity was considerably more narrow. Baron Wilhelm Gottfried von Leibniz strode the European landscape with the supreme confidence, and a number of good reasons for it. As a German diplomat and mathematician, Leibniz was so successful that Voltaire characterized him as the epitome of optimism. Worldly, outgoing, quite a fellow with the ladies, Leibniz had nothing in common with Newton, except the discovery of the calculus. There was plenty of room on Newton's plate for a little kindness. After all, he had created the laws of motion, the law of universal gravitation, the reflector telescope, a theoretical explanation for light and color. The menu of his unmatched accomplishments was extensive, to say the least. And yet, despite so much intelligence, Newton permitted, if not encouraged, a bitter controversy with Leibniz. This episode, only one of the emotional dramas in the mechanical universe, threatened the reputation of one man, and the sanity of another. But it will also illustrate one of the curious paradoxes that lurk within the human heart of science. For example, while the scientist isn't always rational, the scientific environment nearly always is. In fact, a physics laboratory is where nature reveals herself in the most rational terms. Compared to Newton, what does the modern scientist really do? Beyond the well-intentioned textbook definition, what's the method of science? And in the real world, how does the scientific method really work? Sometimes it begins with a small beaker of oil, a sturdy iron pot, a dash of discipline, a measure of creativity, and perhaps a touch of genius. And sometimes, although very rarely, the result is as significant as the value of the charge of the electron. Who was this physicist? And by what painstaking means did he become one of the more famous men in scientific history? Past, present, and future, physicists are forever fascinated by the mysteries of nature. For example, the mysterious nature of light. Light. The very idea has been as hard to grasp as the almost incomprehensible vastness of the universe, and its speed has been even harder. Why does it have a specific value? Why is it called a fundamental constant? And precisely what is a fundamental constant of nature? Henry Cavendish knew the answer when he measured Newton's universal gravitational constant. In the process of finding it, Cavendish not only weighed the expanding British Empire, he weighed the entire planet. How in the world did he do that? Well, not by hanging out in a pool hall. These men lived by laws that, if not exactly legal, are nonetheless well within the laws of classical mechanics. Of course, not every man here fully appreciates that fact. Most walk down Chalky's narrow stairs to shoot a stick or to profit from the experience by some other means. But odds are, when certain laws of physics are applied just right, every man here fully appreciates the effects. The effects depend on the law of conservation of momentum. And like the game of billiards, it happened to originate in France. In the early 17th century, René Descartes grew up to love mathematics as the workings of God. And as a philosopher, he sought an explanation for all worldly phenomena. In the process, Descartes not only conceived the conservation of momentum, he discovered analytic geometry. With that discovery, he changed forever the terrain of mathematics. How, by one vehicle or another, do great scientific explorers approach unknown terrain? And when something has been discovered already, how can someone else sail right in and claim the credit? Whatever the science, from electricity to mechanics, credit sometimes goes not to the first to make a great discovery, but to the last. Surely this was true in the case of James Prescott Joule, who was far from the first to explore the realm of energy conservation. He might have been the 8th or 9th scientist to come across the law of conservation of energy. But like Columbus, Joule got the credit for discovery. Why? And in the greater scheme of things, why does it really matter? In the storehouse of the cosmos, the shelves are as amply stocked with energy today as they were the morning the universe opened for business. On the other hand, If energy is never lost, why do muscles get tired? And why do masses fall? Mechanical energy, like exercise in general, has a lot to do with speed and position. For a different perspective on changing positions, catch the drift of the good ship Irish Coffee, a challenge if there ever was one in the mechanical universe. Sophisticated electronics, state-of-the-art tracking devices, personnel beyond compare. These are the resources of the United States Coast Guard. Also, behind the scenes, there are the tools of vector analysis. In a crisis or a classroom, how can vector mathematics go to the rescue? In the serious world of science, vector mathematics can accomplish miracles. So the question is not whether it can come to this rescue, but whether it really should. Put another way, is this music? Or is it Memorex? In any case, a classic Memorex commercial clearly illustrates both excellent reproduction and the physical phenomenon of resonance. What is resonance? How are its many forms heard from throughout the mechanical universe? And why does a mere human voice, even one as powerful as Ella Fitzgerald's, produce such shattering results? And in the even greater atmosphere of the mechanical universe, what are some other forms of sound and fury? This trio undertook a journey that surpassed every earthly explorer since the first primitive step into the unknown. Their destiny had been determined by engineers and scientists, technicians and visionaries, researchers and test pilots, by the best laid plans and all the right stuff. But like the rocket itself, a straightforward question arose. How is it possible to get from here to there? Historically speaking, rockets don't go anywhere without a pretty good plan behind them. And even today, they don't get very far without classical mechanics. Who are the space navigators? Beyond the everyday world, what do they seek? And often surprisingly, what do they find? From Johannes Kepler onward, celestial scientists could calculate the motions of the solar system. But the miracle of the space age is making heaven passable as well as possible. While that might have been what the father of classical mechanics dreamed of, it's what the space navigators do. In a sense, all scientists are navigators and explorers. The quest, in one way or another, has always been human destiny. The strategy has always had something to do with teaching and learning, with imagination and logic, with trial and error, with taking risks and going to the limit. Not only the strategy, but the universe itself may turn out to be some sort of cosmic game. Over the years, the roster has included some very impressive players. Some played by the rules, and some made up their own. But all of them shared a common need. They had to play the game. It's been played for the highest stakes and for the longest time. And in a sense, the game will never be over.
I think that our subject, classical mechanics, is part of the most important discovery in human history. Before it was made, our view of the universe was the one that we received from the ancient Greeks, mainly in the words of Plato and Aristotle. In that view, the crystal spheres of the heavens were immutable, serene, eternal, and perfect. Only down here, on this lowly earth, was there confusion, decay, disorder, and death. It was a view that was literally designed to put us in our places. But that place, the earth, was at the center of the universe, and we could easily imagine ourselves to be the purpose of creation. Then along came Copernicus and Kepler and Galileo and Newton, and by the time they were done, we lived on a speck of dust in a forsaken galaxy in a lost corner of the universe. No matter how lowly Plato and Aristotle had tried to make us, never in their wildest dreams did they think of doing that to us. Life today is not very different from what it was 2,000 years ago. In its essentials, the human condition has not changed very much. But in that one thing, it's changed forever. We've discovered our place in the universe. That's why the discovery is so important. Our job is to find out what that discovery was, how it was made, and by whom. And we'll begin with one of the most important discoveries by Galileo Galilei when we meet here next time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.